Okay, so yeah, thanks for inviting me. I was asked to give a tutorial on number in hand communication complexity or message passing communication model. I know that several of you have seen this large parts of this talk before, so yeah, so let me start. So in the k-party number in hand model, we have these k players, p1 through pk, who have respective inputs x1 through xk. And the goal is just to compute some function f, and we'd like to minimize the total communication complexity. Okay. Here we have point-to-point communication between every pair of players. And we also have that the protocol transcript determines who speaks next. Okay, so it says who starts, who sends the first message. This message is sent to someone, and then that player determines, sends a message to the next player, etc. We're going to introduce a simplification, which is it's convenient to introduce a coordinator C, which is this extra player which may or may not have an input. And what we're going to require is that all communication goes through the coordinator. Okay, so the coordinator talks to a player, the player responds, the coordinator talks to the next player, etc. And this only affects the communication by a factor of 2, right? So now instead of a player directly talking to another player, it's passed to the coordinator and then to that other player, plus a word per message to for the player to indicate where to send this message to. These factors will be small, and I'll ignore them for this talk. Model motivation. So as we've seen, motivation for these kinds of things earlier today, when your data is distributed, stored in the cloud, you want just maybe for speed reasons, if you have sensor networks or network routers, the communication may be very power intensive and you have bandwidth limitations. So here you really want to minimize communication. There's this field distributed functional monitoring developed by several people in this room, where the coordinator wants to continuously monitor a statistic of distributed data, and you don't want it to be the case that every time data is changing on one of these players that you inform the coordinator of this change. This would require a lot of communication. And if you prove lower bounds in this number in hand model for the static case, then you get lower bounds for the dynamic case as well. So just formally, randomized communication complexity, R of f, in this model, it's the same as you're used to. So the communication cost of a protocol is the sum of all individual message lengths between the coordinator and players, maximized over the inputs and the random coins. And R of f is the minimal cost of a protocol, which for every set of inputs fails in computing the function with probability at most, say, 1/3 over the random coin tosses of the players. Yeah. Okay. So yeah, for the outline of the talk, I'm going to go over problems in different areas. I'll start with database problems, and I'll focus on a statistical problem here called distinct elements, which illustrates several ideas in this model, including sort of symmetrization, which is a technique developed by Qin and his colleagues. Also composition. So what is here? So here, think of these xi's as being vectors. And what we're interested in is properties of the sum vector. Okay, so x is the sum of the vectors over the players. And one function that's been studied repeatedly in the data stream literature is the p-norm of the vector x. Okay, so yeah, the sum of pth powers of x to the 1/p of the coordinates, and interpreting 0 to the 0 as 0 and non-zero to the 0 as 1. When p is 0, we can define this to be the number of non-zero coordinates of your vector x. Okay, so this has a natural application. If these vectors xi on each of the players are binary, then it's just the characteristic vector of a set that that player holds. And when we look at the zero norm of the sum of these vectors, this is just the size of the union of all of these sets. Okay? Okay. Yeah, so I'm going to discuss how hard is it to compute the size of the union, the number of distinct values. Okay, so first, as you're used to in this area, exact computation of the number of distinct elements requires a lot of communication. So you can show that there's a linear and n randomized communication complexity lower bound already for 2 players. Okay, and this is a direct reduction from the set disjointness problem. So just to go through it to introduce notation that we'll use later, you have 2 players, Alice and Bob, with sets S and T from a universe of size n. And in the disjointness problem, they're promised that either S and T are disjoint or they intersect uniquely. Okay, and so we're going to say that if they intersect, then the disjointness function evaluates to 1, and if they don't intersect, this disjointness function evaluates to 0. And do you guys see the, so there's a reduction to this problem. Do you guys see the reduction? So what we're doing is we're saying compute, the number of distinct elements is the union of S and T, right? And this problem is saying it's hard to compute the intersection size. And it's easy for the players to exchange the sizes of their sets, right? So yeah, so that's the whole reduction, right? So yeah, Kalyasunam and Schnitger, and simplified by Razborov, showed there's a linear and n lower bound for randomized complexity. And yeah, using what I just said, the union size is the sum of the 2 set sizes, but you overcount the intersection. So then you can just figure out, you can solve disjointness by solving this exactly, right? Okay, so because of this, we should focus on approximate answers. So we want to achieve relative error, so we want to output a 1 plus or minus epsilon approximation to the union size. And the question is, yeah, what is the randomized communication cost as a function of the number of players, k, the accuracy epsilon, and this universe size n? Okay. And I do want to note that here it's important to understand the dependence on epsilon. Okay, as in a lot of streaming works, people study this. If epsilon is 1% and the dependence is 1 over epsilon squared, that's a lot worse than if the dependence were 1 over epsilon. Okay, so let me just give you an upper bound to show you what a target would be for a lower bound. So the upper bound is just going to come from running a streaming algorithm. Okay, so the first player will run a streaming algorithm and send the state to the next player, who will then send it to the next player, etc. And so they're just going to run a streaming algorithm for estimating the number of distinct elements in the stream. Okay, so yeah, so the player I interprets its set as the ith set in a data stream. They run the streaming algorithm, and it's known that there's a data stream algorithm for estimating the number of distinct elements using only 1 over epsilon squared plus log n bits of space. Okay, so this is in work with Kane and Jelani. So using this reduction, this gives us a protocol with k over epsilon squared plus k log n bits of communication. Okay, so it's significantly better than the exact case, right, where we required at least n bits of communication. Yeah?
So here you don't care about the number of rounds, you just...
Yeah, so this, for now, I'm just going to talk about total communication. I'll mention like round complexity as an open question towards the end of the talk. Yeah. Okay. So yeah, it turns out that this approach is actually optimal. That you can show a k over epsilon squared plus k times log n communication lower bound. I'm going to focus for the most part on this k over epsilon squared part of the lower bound. This was developed with Qin Zhang a few years ago, and it really also uses very interesting techniques by Phillips, Verbin, and Zhang. Okay, so yeah, so how are we going to prove this k over epsilon squared lower bound? So let's start with a simpler problem that I'll call the gap threshold problem. Okay. So let's look at this problem. So here, player, instead of holding a set, pi just holds a bit, zi. Okay. And actually, now we're going to put a distribution on the inputs. Okay, instead of being worst case. These bits are going to be fair coin tosses. And the coordinator is going to try to decide one of these two cases. Is the sum of the k bits at least its expectation, k over 2, plus a standard deviation, root k? Or is it most its expectation, k over 2 minus a standard deviation, root k? Okay, if it's not in one of these two cases, the coordinator can output anything. Okay. So how hard do you think this problem is? Like, what kind of protocols can you do for trying to solve this? So sort of one natural protocol that comes to mind is the coordinator could sample a few players and try to use the number of ones in the sample to estimate to figure out which case they're in. But you can show that sampling doesn't work. For this to work, you need basically to query a constant fraction of players. But formally, how would you prove an omega k lower bound for this problem in this model? Okay, so this is what we'll look at now. I have a slide here on the rectangle property of protocols. Are people all familiar with this, or are people generally familiar with communication complexity, rectangle property?
Don't assume. No.
Don't assume.
Too many people.
Too many people. Okay, so let me just go through it then. So suppose you have a deterministic two-player protocol, and the players have inputs x and y respectively. And it's a protocol for some problem. And on these inputs, since it's deterministic, the first player sends this first message M1. The second player responds with M2, then M3. And suppose I had a different set of inputs, A and B, and I had the same messages being sent between the players. Okay? Then actually what you can say is, so if these two pairs of inputs cause the same transcript, which is defined to be the sequence of messages, then actually so do these pair of inputs, x and b and a and y. Okay, and this just follows basically inductively, right? Like the first player sends this message m1, which she would have sent had her input been x or a, and then the second player responds and basically doesn't know if M1 is coming from X or A. And so this is why you get the cross terms. Okay? You get exactly the same sequence of messages. Any questions? Okay, good. Yeah, so for randomized protocols, the analogous thing is that basically what you do is you just think of the private randomness of the players and include that as part of their input. Okay, and then apply this argument for deterministic protocols. So for randomized protocols, the analogous thing is that the probability that you see a transcript tau given inputs A and B, the nice thing is it factors into a product of two functions, okay? So it's a function P of the input A and the transcript tau times a function Q of the input B and the transcript tau. Okay, so this is a product property which in the case of, so these functions are between values between 0 and 1. In the case of deterministic protocols, this would give you a rectangle. Okay. Okay, so we're going to use the rectangle property as follows. So we want to analyze this gap threshold problem. And the main claim here that makes this work is the following: that fix protocol transcript tau, then actually it holds that these bits z1 through zk are independent, conditioned on the transcript tau. Okay, for any transcript tau. So these bits z1 through zk started off as being independent and uniform. And then we ran this protocol, and we got some transcript. And now we look at the transcript, and we look at the set of inputs that could have gone to that transcript. And the claim is that these bits are still independent, even though some of them might be fixed, right? I mean, maybe the protocol reveals the first bit. It's fixed, but it's still independent of the remaining bits. I'm not claiming there's still Bernoulli 1/2. Okay. Yeah, so just to see this, I mean, it's an application of the rectangle property. We can assume the players here are deterministic by Yao's minimax principle, right? Because there's an input on the distribution, so there's some fixing of the randomness, which is good for that distribution. Now, what is the input to the players in this case? So it's a bit vector of length k, right? These k coin tosses. And it gives rise to a transcript tau, the set of things that go to this transcript. And the claim is just generalizing this two-player rectangle property that I described on the previous slide, that actually the set of inputs that go to a transcript tau has the following combinatorial rectangle structure, that it's the set of preimages of tau is S1 cross S2 cross SK, where each SI is a subset of 0, 1, right? The inputs to the ith player, a non-empty subset. Okay? Any question? Okay. Yeah. So yeah, since the Zi started off as being independent coin tosses, now we condition on them landing in a set of this form. Now, so just look at like the preimages of this transcript. Well, you can see that they're still independent, right? So like what are the options for S1? It can be either the singleton 0, the singleton 1, or 0, 1. And what does that mean? Well, it means that if I look at any fixing of this suffix, then I have a 0 here for that first coordinate, and I also have a 1 here for that first coordinate, right? So this implies, I mean, you can show that these things are independent, right? Any questions? Okay, good. Yeah, so in fact, that's what will happen, right? Some of these SI will be fixed to 0 and 1, and the remaining will just be 0, 1. Okay, so let me just say again where we are. So this gap threshold problem, these Zi are these independent coin tosses, and the coordinator wants to decide if the number of coin tosses is at least k over 2 plus a standard deviation, or at most k over 2 minus a standard deviation. And what we've just shown here is that the bits conditioned on any particular transcript are independent. And what this means is it's equivalent to fixing some of the bits to be 0 or 1, and the remaining are Bernoulli 1/2. Okay. Everyone's following? It's good. Okay. Question? Okay. Okay, so now like this is the main property we use, and I can just give the proof on a few slides. The first lemma in the proof is what I call unbiased conditional expectation. Okay, so what I'm saying is with probability 2/3 over the transcript tau. So first of all, what does that mean? It means I choose a uniformly random input, and by this deterministic protocol, it induces a transcript. And I'm saying with probability 2/3 in that distribution, we have the expected sum of the condition bits doesn't deviate that much from its original expectation, which was k over 2 before you started the protocol. Okay? Now, this is not true for every transcript. There could be some transcripts which really bias the expectation, but it's true typically. So why is that? Okay, so yeah, here's the whole argument. Fix any transcript tau. We said these bits conditioned on tau are independent. So what is the sum? What is the variance of the sum of independent bits? Okay, it's always at most k. Okay, no matter what these bits are. Okay, so if it were the case that this expectation were very far away from k over 2, say like more than 100 root k away, then what would happen is we could sample a random transcript. We would be more than 100 root k away from k over 2. And then we could sample a random input going to that transcript. And by Chebyshev's inequality, we're going to be within about root k of our new expectation with constant probability. So that's a problem, right? Because we know that these original bits, these zi's, if we just take k independent coin tosses, they're going to be about k over 2 plus or minus root k. Now, what's one other way of generating random k bits? Well, you can choose a random transcript, and then you can choose a random set of k bits which go to that transcript. In both cases, we should get the same thing, that typically the input that we get has about k over 2 plus or minus root k ones. But if this were false, then with constant probability, we'd be about 100 root k away from k over 2 in our expectation. And then by Chebyshev's inequality, when we choose a random input going to that transcript, we'll be only about root k away from that expectation, right? So we're like k over 2 plus 100 root k, and then we move about root k away. But that's way too far away from k over 2. Okay? So this means that actually for a typical transcript, when you condition on it, the expectation is still close to k over 2. Is that clear to everyone?
What is typical transcript?
It just means with probably 2/3 over the choice of transcript, where the choice of transcript, the transcript distribution is obtained by choosing a random input, running the protocol, and looking at the transcript that you get.
What's not typical transcript?
I'm just saying, like, you have this transcript distribution, and with 2/3 probability mass under that distribution, you have this property, that the expectation is about k over 2. An atypical transcript might be maybe you check if the first 100 root k inputs are all 0, and it just happened to be that was the case. In that case, your expectation would be really biased.
Yeah, that's what I was thinking.
Yeah, but that doesn't occur that often, right? So that's the point. So basically, with probably at least 2/3 over the transcript, you get this property. Okay. So that didn't use anything about the total communication, actually. That was just a general property. The second lemma, which I call lots of randomness after conditioning, does use the fact that it's a low communication protocol. So basically, it says if the communication were much less than k towards a contradiction, then actually, with large probability over the transcripts, for most of the conditioned bits, there's still IID coin tosses. Okay? It just says that, what did we say on the previous slide? We said that when we fix the transcript, these zi given the transcripts are either fixed to 0, fixed to 1, or uniformly random coin tosses, right? And I'm just saying that most of them have to be uniformly random coin tosses. Why? Well, you have 2 to the k total inputs, right? If your communication is little o of k, this means that you have at most 2 to the little o of k transcripts, which means that for a typical transcript, you have many inputs going to it. You have 2 to the k minus little o of k inputs going to the same transcript. If I'm fixing all of those bits, then I don't have enough inputs going to that transcript. So that's why most of them still need to be Bernoulli 1/2. Okay? Do these two lemmas make sense? Because this is the next slide will complete the proof. This is all. So what we're going to do is we're just going to fix a typical transcript, meaning one for which the expectation of the sum of the bits is still about k/2, and one for which most of the bits conditioned on the transcript are still independent fair coin tosses.
Sorry.
Yeah.
So you, I think on the last slide, maybe you already explained this, I missed it. You said the zi's after you condition on tau, some are fixed.
Yeah.
And the others are Bernoulli 1/2.
Yeah.
So the ones that aren't fixed, you know they're independent. Why do you know that they're still Bernoulli 1/2 and not something else?
Oh,
You said that on the slide before.
which slide?
This one, yeah.
Yeah, they're independent.
Yeah, so oh, the previous one?
Because it's S1 cross S2, right? So
Yeah, so this is the combinatorial rectangle that you get actually.
Oh, okay, sorry, okay.
Yeah. Any other questions?
On that slide, previous slide. No, at the bottom of the previous slide, I think you made a statement. Yeah, the right at the bottom.
Yeah, and then
Okay.
he proved it on the last slide. Yes.
Oh, okay.
Yeah, sorry. The justification was on the previous slide. Yeah, yeah. So. Okay, so yeah, so we have a typical transcript. Yeah, keep that in mind. Okay, so yeah, let's condition on a typical transcript. And now the whole proof is coming from an anti-concentration argument. Okay, so what is the argument? Okay, so what I claim is that forget about the typical transcript having its expectation somewhere. Just use the fact that when I condition on the transcript, most of the bits are still IID Bernoulli 1/2. Okay, what does that mean though? Well, it means that actually there's some anti-concentration to that binomial distribution, right? So if I have a binomial distribution, I'm going to be, a large constant times root k away from my expectation with some reasonable probability. I mean, it's small, but it's a small constant probability. I will be any constant times root k away from my expectation if I have at least k/2 random coin flips, which I do because I have this typical transcript. Okay, but that's a problem, right? Because what it means is that once I condition on tau, it's still the case that this sum of these bits is going to be at least 100 root k larger than its, sorry, in this case, it's 100 root k smaller than its expectation with some small constant probability because of the anti-concentration. Analogously, this sum will be at least 100 root k larger than its expectation with some small constant probability. Okay, but now that's a problem, right? Because we know what its expectation is. Its expectation is at most 100 root k. If I'm deviating on both sides, its expectation is k/2 plus or minus 100 root k. If I'm deviating from my expectation by more than 100 root k, then I'm switching my side from k/2. Then I don't know if my sum is less than k/2 or greater than k/2. So I actually can't solve the problem, given the transcript. Yeah, so actually this should be like 101 root k. 101 root k, because then I'm 101 root k away from my expectation, which is 100 root k away from k/2. And now I can't figure out which of the two cases I'm in. Yeah? Okay, so this means the protocol must err with this probability. So it's the probability of choosing a typical transcript, which is like at least 2/3 times this probability. So some small constant probability, the protocol just fails. Any questions?
the 1/epsilon² comes from the sampling power, the k/epsilon².
Oh, sorry. I mean, there's still a lot of work to get there. So this is just looking at the gap threshold problem and just saying that I need omega k communication to figure out which of these two cases I'm in. I haven't explained how that's used yet. Yeah, so we're just saying, yeah, just one more time, that the expectation is close to k over 2. Yet when I condition on the expectation, I still have many independent coin flips. So I have some, standard deviation, and I'm away from my expectation with good probability, which means I can't determine the answer. OK, great. OK. I should just want to mention some generalizations without proof. So it generalizes when the zi are not necessarily Bernoulli 1/2. And now the coordinator wants to decide, I mean, they're still independent. The coordinator wants to decide if the sum of the bits is at least beta k plus root beta k, where the coins now have bias beta, or at most beta k minus root beta k. You still get an omega k lower bound. It also generalizes to the case when the players have internal randomness. So basically, what you can show here is that any successful protocol, what it must satisfy is a more fine-grained statement that basically, for a typical transcript, the probability over transcripts tau, it must be the case that when I condition on tau, most of these bits, they started off as having entropy 1. They were fair coin tosses. But after I condition on tau, most of them must have entropy which is significantly less than what it started with, OK? So little o of 1. Because otherwise, I can perform a similar kind of anti-concentration argument. OK, so yeah, what was all this for? So we want to get this lower bound for approximating the union size. And now the idea is to use what I call composition. So what we're going to try to do is take that problem we just studied and embed it into a larger problem. So let me say what that means. So let's consider the following problem. It's again, there's an input on the distribution. The coordinator is going to have an input. The coordinator's input is a random set S from the domain 1 through m. OK? And now each of the players is going to have input a set, ti, instead of a bit. But what we're still going to do is think of generating these k bits for gap threshold. Just think of them as some auxiliary bits. We're generating them. We're flipping them. And we say, oh, if I flip the ith bit and it was 1, then what I'm going to do is I'm going to give player pi a random set ti which intersects S in a uniquely random position. And I say, oh, if my bit flip was 0, then I'm going to give player pi a set ti which is disjoint from the set S, uniformly random disjoint set. OK, so these zi's are not actually inputs to this problem, but in some sense they define how these inputs are being made. And what is this composed problem? Well, we're going to ask the following. Is the number of disjointness instances between S, the coordinator set S, and the player set ti, is the number of them that evaluate to 1 at least k over 2 plus root k? Or is the number of them that evaluate to 1 at most k over 2 minus root k? OK? And we have these bits zi in mind, which were used to generate the inputs. So it's equivalent to our earlier gap threshold question. Is the sum of the bits zi at least k over 2 plus root k, or at most k over 2 minus root k? I should note that, notice that all these disjointness problems are heavily correlated, right? Like, so you can think there's a disjointness problem between the coordinator and the first player, the coordinator and the second player. The coordinator has the same input set to all of these disjointness problems. And what we can show here, though, nevertheless, is that there's a total communication lower bound of m times k. OK, so m is the size of these sets, and we have k players. So even though there's this input overlap, the same input to all the instances, it's still an m times k lower bound. And I should note that this really uses the fact that we're in this number in hand model. if we were in some other model where you could just post onto a blackboard or a broadcast channel that everyone could see, then the coordinator just needs to post his set S, and everyone could figure out if it intersects or not. So you'd only have M communication. But here, we get M times K.
Yeah, I just want to point out that this problem looks very similar to a problem that Piotr mentioned earlier today. But that was one-way communication, and like here, it's like a bunch of disjointnesses with related one of the inputs. One of the inputs is fixed to be X. But it's sort of a threshold version too, like that sort of unique version, the predicate version. Sorry, just a remark.
Okay. Good. Okay. So how do we show this? Well, we know that this gap threshold problem is sitting inside of this problem. Right? The bits Zi are the outputs, the answers to the disjointness instances. That's how we generated the inputs. Okay, so what this means, though, is that actually, if I have a correct protocol for this big composed problem, then what do we say? Well, we say that for a typical transcript tau, if I look at the transcript tau, it has to reveal a lot about these individual bits, these Zi's, because gap threshold is sitting inside of this problem. In particular, the entropy of most of these bits Zi needs to be reduced, condition on the transcript. Okay, but this is interesting, because what does it mean for the entropy of this bit Zi to be reduced? I mean, what does it mean for Zi to be mostly determined from the transcript? I mean, intuitively, what it means is that most of these disjointness instances are actually solved by the protocol. I can look at the transcript, and I can figure out what Zi was. And so I actually solved the ith disjointness instance. Okay. So how do you formalize this? Or how do you get a lower bound out of it? Okay, so let's suppose towards a contradiction that the total communication were much less than k times m. Okay? So this means that actually, by averaging, there's a player pi which has two very important properties. The first is that the communication between the coordinator and pi is much less than m. Right? The total communication is k times m. And so if it's much less than k, if the total communication is much less than k times m, there are k players. Typically, between the coordinator and one of these players, the communication is much less than m. Now, the second thing is, we know that for a typical transcript, most of these input bits have their entropy getting reduced. So what it means is that now this Zi is the output of the disjointness instance between the coordinator and the ith player. So what it means is, for a typical transcript, there's an I for which, for most typical transcripts, its entropy gets reduced. Right? This is saying for a typical transcript, a large fraction of the Zi's are determined. In particular, this player Zi is typically determined. So what we're saying is there's a player which has low communication with the coordinator, and for which, if I look at a transcript, it's typically the case that I can figure out this bit Zi up to some error, small error. So a union bound gives you both of these simultaneously. So let's fix this player, this good player. Okay, but then the proof can be completed on this slide. So the point now is to reduce this to a two-player problem and contradict the two-player communication complexity of disjointness. Okay, so how do we do that? Well, suppose we have two players in our two-player disjointness problem. They each have input sets. One of them is going to pretend to be the coordinator in this k-party protocol. And the other one is going to pretend to be this special player, pi, that we fixed on the previous slide. And now, how do we generate the inputs to these players? to the remaining players. Well, what did we say? Well, we said we look at this set S, this input to the coordinator, and we said, oh, we just flip a bunch of random independent bits. We said if Zj is 1, I choose a random set which intersects S, and I give that to the jth player as input. If Zj is 0, I choose a random set which doesn't intersect S, and I give that to the player. So actually, this coordinator here can generate inputs for all of the other players except Pi locally, from just using the knowledge of his input set S. Okay, now we have these two players trying to solve disjointness, and they're going to run this k-player protocol. But the point is that actually the messages between the coordinator and any player Pj other than the ith player, they can all be simulated locally. Right? I mean, this coordinator has all the inputs for these fictitious players, all the inputs for these players in this k-party protocol. So every time there's a message, he just simulates it locally, and you don't actually pay communication. So the only communication you pay is actually between the coordinator and this player Pi that we fixed on the previous slide. But what did we say? Well, we said that the communication between the coordinator and Pi was little o of m. So what we're doing is we're actually solving disjointness with little o of m communication for two players. Right? Because we also said that from the transcript, you can typically figure out the answer to disjointness. But that's a contradiction, right? As I mentioned earlier, there's an omega m communication lower bound for two-player disjointness. Now there's some things that Sure.
Where did you use the gap, the square root k gap business?
Oh, the square root k gap business. Yeah, so sure, okay, so we said, how do we generate the inputs to, so this compose problem. So how do we generate the inputs to this compose problem? We said, okay, in our mind, we're going to generate k random bits, zi's. These were the inputs to some gap threshold. And we're going to say, if zi is 1, then what we're going to do is we're going to give player Pi a random set Ti which intersects the set S. And if it's 0, then we give it something that doesn't intersect. Now since this, and then what we said is, this problem, you want to figure out the number of disjointness instances that evaluate to 1 is at least k over 2 plus root k, or at most k over 2 minus root k. But the way that this was generated, this is equivalent to saying, is the sum of these bits zi at least k over 2 plus root k, or at most k over 2 minus root k? And we say we have a correct protocol for this, so we can figure out if the sum of the zi's is at least this, or at most this. But what we said before is that for any correct protocol that can figure out if the sum of the zi's is at least this, or at most this, it must reduce the entropy of most of the bits zi given the transcript. You got it? Yeah.
On the last slide, when you say give player Pi, on the previous slide, when you say give him a random set Ti such that disjointness is either 1 or 0, it's according to the hard distribution for disjointness.
Yeah. So that exactly. So I did hide stuff under the rug. Like we're proving a distribution. Ultimately, we're contradicting a distributional lower bound for disjointness, and it's actually with expected communication. And so there's a hard distribution there, and we can use the hard distribution in the paper given by Rezborov. But I wanted to hide those details. Like we're ultimately contradicting a distributional lower bound. Okay. Yeah, so, sorry, where was it?
One question.
Oh, yeah.
In that slide, when you generate all the other players locally,
Yeah.
how do you ensure the promise that it has to be greater than square root k, like, or minus less than?
No, but that happens with large probability, actually. Yeah, so it is typically the case that if you generate, yeah, okay. Yeah.
In the previous slide, could you explain the union bound part again?
Oh, sure. Yeah, so suppose the communication were much less than little o of km, right? This means that for a random player, for almost all of the players, the communication is much less than little o of m. So in particular, for a 2/3 fraction of the players, the communication is much less than little o of m. And we also know that for a typical transcript tau, for say a 2/3 fraction of the bits, the entropy of the bit conditioned on tau has been reduced. And now by union bound, you have an I with both of these properties. Yeah.
So this protocol finally solve the intersection, answers the intersection between the tape layers?
No. So that's the next slide. So this is so we started off with gap threshold. This is this composed disjointness problem. And now I'm finally going to say how you get a lower bound for approximating the number of distinct elements. OK. And that's, sorry. OK, so that's this slide. So how do you do it? So you're going to set the universe size of these sets to be 1 over epsilon squared, where we call you 1 to 1 plus epsilon approximation. And as I said, the proof generalizes to other values of beta with still an omega k lower bound. So what you're going to do is you're going to set the probability beta of intersection to be this quantity, 1 over 4k epsilon squared. Now, first of all, this might not always be a probability. Like, it might be larger than 1. So this talk, I'm just going to focus on the case when actually k is larger than 1 over epsilon squared. So this is at most 1. It's a probability. And then this lower bound that I just described goes through. There are other things you can, so yeah, in follow-up work with Qin, we were able to show even when k is small, you can get this lower bound. OK, so what happens when I set the probability beta of intersection to be this? So if I plug this into here, then this becomes 1 over 4 epsilon squared. And this becomes 1 over 2 epsilon. So actually now the standard deviation is equal to epsilon times the expectation. Yeah? So this is the intuition why a 1 plus epsilon approximation would be able to distinguish these two cases. Yeah, so let me, on the next slide, say why now approximating this union size up to 1 plus epsilon solves this problem. OK, so let me just say the reduction. OK, so we have this input to this composed disjointness problem that we've been discussing, right? And we said that there's a k times m lower bound, where m is the universe size. And now we said for this, let's set the universe size to be 1 over epsilon squared. So there's a k over epsilon squared lower bound for this problem. And let's get a k over, let's reduce, let's show how if you can estimate the number of distinct elements, you can solve this problem. So the reduction is as follows. The coordinator has this set S. And in the distinct elements problem, he's going to think of instead having the complement of that set. OK, 1 over epsilon squared without S. And now the main point here is what happens if the disjointness between the set S and Ti, the ith player's input, what happens if it's 0? That is, that they're actually disjoint. Well, then this set Ti is entirely contained in the complement of S. So if you think about this from a distinct elements perspective, what happens is the coordinator first inputs this set into the total number of distinct elements. And then every time that S is disjoint from Ti, no new distinct elements are created, because they're all contained in this set that the coordinator already introduced. It's clear? OK. On the other hand, what happens if S does intersect Ti? Now we said in our promise they intersect uniquely. Well, in that case, Ti is going to add a new distinct item to what's already there, right? Because it's not entirely contained in this complement. There's one item that's not there. So one new distinct item gets introduced. Now there is some technicality that sometimes, yeah, so now if I have Ti intersecting S and Tj intersecting S, they each introduce a new element. And maybe those two elements are the same, but typically they're not. OK? So basically, most of the time, these items are not. And so you can basically, for this talk, you can handle the, so just think of them as introducing a new distinct item. OK? It's very easy to handle the case when they intersect with very small probability.
Is this the only place where you use the randomized
I mean, the whole proof is distributional, basically.
understand, but
Yeah.
is this the reason? This is
No, I mean, we use it just for like the basic arguments before required a distributional, I mean, generating
the
inputs
same arguments would have been carried through.
for randomized, I don't know. Okay, so let's see what happens here. So what is the total number of distinct elements? So the coordinator introduced the complement of his set, which was a random set. So you got about 1/2 epsilon squared distinct elements from that set. And then every time one of these disjointness instances evaluated to 1, you got one new distinct item, up to this small possibility that the two items collided. So that means the number of distinct elements is 1/2 epsilon squared plus the sum of the bits zi. But the sum of the bits zi, we said, well, it's 1/4 epsilon squared plus or minus 1 epsilon, depending on which case you're in. That's how we set the parameters. So therefore, this quantity is different by a 1 plus epsilon factor in the two cases for this composed disjointness problem. Does it make sense? So that's the whole proof, right? So therefore, this requires k over epsilon squared bits of, total communication. Okay, good. No questions. I'm going to move on to something else. Yeah, so let me just wrap up. So the overall lower bound is k over epsilon squared plus k log n. I didn't describe the k log n, but it also is a reduction from a two-player problem. And this time it's a reduction to a two-player equality problem. Now, two-player equality in the private coin model, in the model we've been discussing, requires log n bits of communication. And if you have k players, it gets more complicated because, so typically when you go from private coin to public coin, you want a player to send a short seed, like a log n bit seed, and then now they both have the seed and they have this long sequence of randomness from the private coin. But now you have k players and you need to send this seed to all k of the players. This is intuitively why the k times log n is coming. Okay. Yeah, so okay, so let me just, for these other areas, I'm just going to mention them briefly. So graph problems. We looked at a problem that turned out to imply lower bounds for a number of graph problems. And so let me just say what that problem is. So there's an n by k binary matrix A. Each player has a column of this matrix. Okay? And you want to know, is the number of rows with at least 1, 1 larger than n over 2? Okay? Equivalently, the number of rows with all zeros is at most n over 2. So for this problem, we can show kn bits of communication lower bound. And it turns out to have a number of applications. So one application is for connectivity. So suppose you have a bunch of players who each hold a disjoint subset of edges of a graph. Okay? And you want to know, if I take the union of all these edge sets, is the corresponding graph connected? So there's a kn upper bound, right? Because the upper bound can be each player locally computes a spanning forest, n edges, and sends this description to the coordinator, who checks if the graph is connected. And this is showing that actually kn is, there's a reduction here that shows that kn is optimal. Also for bipartiteness, you can get, testing if a graph is bipartite, you can get a kn lower bound.
Is there any restriction on the range of k?
Let's see. So we didn't consider k to be very large, but let me think if that what would it mean? I think this should go all the way up to k. Yeah, there doesn't seem to be any restriction. Yeah. Just make sure. Yeah, I think that's right. Yeah. Linear algebra problems. Okay, so in this model, you have k players which each have an n by n matrix over a finite field of size p. And the problem is, the players want to know, is the sum of their matrices invertible? Okay, that's the whole problem. So do you guys know what have a guess for what the complexity of this problem is? What's that? So, what's that? You should not be guessing. Yeah. So yeah. So basically, there's a kn squared log p lower bound for this problem. So that basically says that you can't really do anything non-trivial, right? So each player has n squared log p bits of information, and they all send this to the coordinator. Is an optimal protocol. There's an open question. Sorry. So this same lower bound also holds for related problems like rank, of course, and solving linear equations. There's an open question here, which is lower bounds over the reals when you impose some sort of bit complexity bound on the entries. So we don't know much about this problem at all, actually. So I think there might be a kn lower bound, but we don't even know an n squared lower bound.
Sorry, what do you mean real?
So what I mean here is everyone, instead of having a matrix over a finite field, has a matrix where the entries are, say, integers of bounded precision, and you want to compute whether or not this is invertible over the reals, the sum. And I think even for two players already over the reals, this problem is open. So I think there's an n lower bound you get just from a reduction from set disjointness, and there's nothing better known than n squared as an upper bound. And the way these lower bounds work is they sort of apply reductions to a two-player problem. And so given our gap in understanding there's a gap in understanding here.
So the reals is represented by bounded precision?
Yeah, say bounded precision. Yeah. Okay. Yeah, so there's a really cool work of Braverman et al. That I'm not going to, I guess I won't have time to discuss too much, but they look at the set disjointness, k-party set disjointness, which is a different notion of set disjointness than we looked at. So you have these k players that each have a set Ti, and they want to know, is there an element that occurs in all of them or not? Okay, and what they showed was a k times m lower bound for this problem. As a very nice work. Okay, I guess we started a little bit late. I can say something about this. So let me just describe what a hard input distribution for this problem would be. So the idea is that you take all the m items and you partition them into two pieces. Half the items are going to occur randomly in each of the player sets, independently. So with very high probability, those items won't occur in all k sets. And the other half of the items are going to occur in all sets except a single randomly chosen set. Okay, so far the input distribution only places measure on instances which these are always disjoint. But then you can think of, with probability 1/2, make a random item that you've already, just make one of these random items occur in each of the TIs. Okay? So this is the hard input distribution. Let me just say, so this is what it looks like, basically. So here, the columns correspond to inputs of the k players. And the rows correspond to items. Okay, so a 1 indicates that the first player has the first item, the first player does not have the second item, etc. We said half of the items occur in all but one player's set. So there's just a single 0 on those rows. And we said half of the items were randomly included independently in each of the player's sets. So we have these random rows. Okay. Now the intuition why this problem is hard is, so the coordinator can query a few players, like the first log n players, just query their sets entirely. It only takes n log n bits of communication. He can very quickly figure out which of the rows are random in this matrix. Right? Because if he sees 2 zeros on a row, he knows it's random. So now he knows what the sort of important rows are, the rows which have at most 1 0. But there's no way for him to communicate this information to the players. Right? So he has the identity of a random subset of rows. This takes m bits of entropy. He can't communicate this to each of the players, otherwise he'd spend k times m communication. On the other hand, from the player's point of view, they look at their input and they don't know which zeros are important. Most of the zeros in their column are going to correspond to these random rows, which don't affect the answer. It's only the zeros that cause a row with all ones except for possibly a single 0. It's only those zeros that are essential to transmit to the coordinator so he can figure out the answer. But the players can't figure out what these rows are. And so, the authors of this paper have a very cool direct sum theorem. First of all, it's cool because it's a direct sum theorem for k players in this number in hand model. And it's also cool in that they look at a mixed information cost measure, which sort of captures how much the coordinator sends to the players and how much the coordinator sends to the players about the identity of the random rows and how much the players send to the coordinator about their inputs. Okay, so so that's set disjointness work. There's also some interesting recent work on more general topologies. So instead of, we've been looking at this clique topology, or equivalently the star topology. So Chattopadhyay, Radhakrishnan, and Rudra study general topologies where the communication cost often scales as the one median cost of the topology. Okay, so you take your k players. The one median cost is a node for which the sum of distances in that topology to that node is minimized over all nodes. Okay, so if I have a star, the one median cost is just k. Or a clique, the one median cost is just k. I choose a node and everyone is within distance 1 of that node. But if I take a line, then the one median cost is actually k squared. And so for some problems, you get k squared communication on the line, but in the star you would only get k communication. And they also looked at other variants where you have a topology, a graph, but only a subset of the nodes actually have inputs. And they want to quickly communicate over this graph to solve a problem. And they show lower bounds that depend on sort of the Steiner tree cost of the nodes that have inputs in this graph. Okay, so let me just conclude. So we mostly looked at techniques for lower bounds in this model via the example of the distinct elements problem. Many tight lower bounds are known in this model: statistical problems, graph problems, linear algebra problems. And open questions in future work. So someone asked about rounds. So round complexity is not very well understood for a number of problems in this model. For instance, if you want to check if two nodes in a graph are connected and you try to do a BFS, this sort of requires a lot of rounds. Connections to other models such as MapReduce, like what happens if I impose a space constraint on each of the players as well. And yeah, there are a lot of questions in these topology sensitive papers too. So that's all. Thanks. Yeah.
Does your gap threshold lower bound not follow from this query complexity lower bound for gap majority? I mean, mean, your model is different, I know, because you have these players who are active entities, but since they only have one bit, I don't see how this is different from this query complexity.
From the query complexity model? So I'm not sure.
And I could be mistaken in the intuition, but somehow the intuition is that since each player has only one bit, they can only do one of two things at each point of time. So how is this different from being this
For randomized communication,
So anyway, you were making your argument for a deterministic protocol.
I mean, in the end, we proved this lower bound for this composed disjointness problem, and so we have randomness that's coming there as well. But are you saying that maybe?
Yeah, so that part of the argument is fine. I mean,
yeah.
I'm just wondering the initial gap threshold lower bound.
If there's a query complexity way of seeing this, yeah, possibly like.
Your argument is almost the same as the argument for the query complexity.
Query complexity.
So I guess it's
Okay. Well, yeah. Let's talk about it. Yeah. Okay.
Thanks, David.